Hello students, good afternoon to all of you. So in my previous video I have explained the three moment equations for continuous beam. So three moment theorem I have explained, and in this video I am making the application of these three moments by doing some numericals. So let's take one by one. So a beam ABCD 16 meter long is continuous over three span. AB is equal to 6 meter, BC is equal to 5 meter and CD is equal to, so this is my beam AB, BC and CD. There are three spans, 6 meter, 5 meter and 5 meter. So there is a point load of 80 kilonewton which is 2 meter from here, and then point load of 60 kilonewton which is 3 meter from D, and this BC carries a UDL of 20 kilonewton per meter intensity. So this is the beam, and this support B sinks by 5 mm. Support B sinks by 5 mm means at this B there is a settlement of 5 mm, means delta is equal to 5 mm. It carries a UDL 20 on BC. This, so calculate the moments and reactions at the supports. I is equal to this one and E is equal to this one. So this is I and E. So as I have explained in my derivations, I have to treat each span separately as a simply supported beam, and I will draw the BMD. This is my free bending moment diagram. So area of this will be, this is the free BMD by treating as a simply supported beam. So this ordinate will be 80 into this 2 into 4 by 6. So I will get 106.67. For this span, by treating the BC as a simply supported, this will be the free BMD for this span, and this ordinate is WL square by 8. WL square by 8 is equal to, W is 20, L is 5 meter square upon 8. So I will get 62.5, and similarly this is eccentric load. So this will be WAB upon L, 60 into 2 into 3 upon L. So I will get 72 kilonewton per meter. So this I will get, this is the ordinate. Now its central distance of this from here, this will be, suppose this is the centroid and this is the x1 bar. So central distance of this point from this, it will be this area, this is the ordinate. So AX bar will be, area will be 1 by 2 into this ordinate into this length which is 6 meter. So this is the area, and X bar will be distance of the centroid from this point. This will be L plus A by 3. The total is 6 meter and this distance is 2 meter. So this centroidal distance will be 6 plus 2 by 3. With this I will get A1 AX bar. Similarly, for this, area of this will be, this is a parabola. So 2 by 3 of this ordinate into this length. This is the area, and its centroid will be at the center. It is symmetrical. So distance from this point, this will be half of this. So half of this will be 5 by 2. With this I will get this one. Area of this will be, this is a triangle. So area will be 1 by 2 into this ordinate 72 into this. This is the area, and its distance if I want to know from this force, so this will be x bar. So it will be L is 5 meter, 5 plus this one is 3 meter. So this central distance from this point, this will be L plus A by 3, 5 plus 3 by 3. So with this I will get Ex bar for this portion. Then I will apply the 3 moment theorem. So this is the ordinate 106.6, 62.5, 72.5, free BMD. This one which I have explained. And for span AB, area is this one. So Ax bar is 853.36. So this will be 853 by 36. And for span BC, Ax bar will be, this is the area, and this will be 520.83. So this, for this portion, Ax bar will be 520.83. For span CD, area is 180 into this. So this will be 480 with D as the origin. With this D as the origin, so this Ax bar for this portion will be 420, 480, 480. So this I will get. Then I will apply the 3 moment theorem. So applying 3 moment theorems for span AB and BC. AB, BC means for this portion. For this portion, so for this treating AB and BC, 2 spans, AB and BC, and applying 3 moment equations for AB, BC span, these 2 spans. So MA into this length, this will be MA into L1 plus 2 MB into L1 plus L2, since EI is constant, plus MC into L2 plus 6 A1 x upon L1 plus A2 x2 bar upon L2 is equal to 6 delta 1 upon L1 plus delta 2 upon L2 into EI. So this is the equation, 3 moment equations. So EI is equal to, E is given in the question, and this is the moment of inertia. So this is the I, and this one is E. So EI will be, after converting this in mm, I will get this ones 19530 kilonewton per meter, kilonewton meter square. This is EI. Delta is 5 mm. This delta is settlement of this point B, which is 5 mm. So this delta is equal to 5 mm is 5 upon 1000 meter, 1 upon 200 meters, and this delta 1 is equal to delta 2. As we know this, so deflection of this point with respect to this point, this is 5 mm, this is delta 1. Deflection of this point with respect to this point, this is delta 2. Hence, delta 1 is equal to delta 2 is equal to 5 mm. Since both are at the level and there is settlement only on this point. So, delta 1 is equal to delta 2, which is 5 mm. 5 mm is 5 upon 100 meter, 1 upon 200 meter. So, now let us put the value in these equations. So, MA is equal to 0. Since this is a simply supported support, so MA and MD is equal to 0. MA is equal to 0. So, this will be 0 plus 2 MB into L1 plus L2 is equal to 6 plus 5 plus MC into L2. L2 is equal to 5 plus 6 A1 X1 upon L1 plus A2 X2 upon L2 is equal to this one. So, A1 X1 is equal to this one and A2 X2 is equal to this one. So, by putting the value in these equations, I will get this one is equal to 6 delta 1 upon L1. Delta 1 is 5 upon 200 meter upon L1 6 meter and delta 2 upon L2 this is 5 meter into EI. So, by putting the values in this equation, I will get this one. So, suppose this is my equation number 1, MB plus 0.2273 MC is equal to minus 57.433. Similarly, 4 span BC and CD. Now, for BC and CD, so if I treat these two spans, I am considering this and this span, and I will apply the 3 moment equation for this BC and CD. So, there is a settlement of 5 mm. So, it will be like this. So, my C will be at the center. C will be center. So, deflection of C with respect to this point, in this case, as the C is upward, with respect to this point, it is upward. So, means deflection of C with respect to this will be minus delta, minus 5 mm. So, delta 1 will be minus 5 mm and deflection of this point with respect to this is 0, as both are at the same level. So, delta 2 is equal to 0. So, it will be like this, as settlement of this with respect to this B is minus 5 mm, since it is against the generalized deflected curves as we discussed in the derivations. So, it is upward means minus 5 mm and it will be 0, both are at the same spot. When I consider this span, then deflection of with respect, this is delta 1, this is downward, so this is 5 mm, this one with respect to this is also 5 mm. So, delta 1 delta 2 is equal to 5 mm. But when I consider this span BC and CD, then deflection this C will be at the center. So, deflection of C with respect to this point, this will be minus since it is upward as against this B. It will be minus 5 mm, and since both are at the same level, so delta 2 will be 0. So when I apply the moment, 3 moments, delta 1 is equal to this one, and delta 2 is equal to 0, and applying 3 moment theorem for equation BC and CD. It will be MB into L1 so MB into this span, MB into this one, plus 2 times of MC into L1 plus L2 plus MD into 0. So this I will get MB into plus 6 A2 X2 upon this one. So area of this will be A1 X1 bar for this when I considered this. So AX for this. So this will be my area of this into this, and for this will be AX for this, it will be from this points. And this, as we calculated, this is 480, this one was 520.83. So I will put this value here. So I will get another equations, and that after solving I will get these equations. So this is my equation number 2, and equation number 1 is this one. So equation 1 and this equation 2, by solving this I will get MC is equal to minus 54 upon 66 and MB is equal to minus 45.01 kilonewton meter. So these are the values. Now so this is my free BMD. This is the free BMD, and fixed BMD will be like this. MA is equal to 0 and MB is equal to, as we calculated, is minus MB is equal to minus 45.01 and MC is equal to minus 54 upon 66. So it will be like this, 54 upon 45.01 MB, and this one is 54.66 and this is 0. So this will be the, and this is hogging. So if I superimpose, this is my fixed BMD, and this is the free BMD. When I superimpose both the diagram, I will get final BMD. So this is the final BMD. So it is 45.01, 54.06. So this one is the fixed BMD, and this one is the free BMD. When I superimpose both the diagram, I will get this portion upper of this will be the net. This is sagging, and this will be hogging. Again this will be sagging, this is hogging, and this will be sagging. So this is my final BMD. So if I want to draw the SFD, then I will require reactions. For finding the reaction at the spot, what I will do, I will calculate the reactions and Suppose I want to know the reaction RA, I will take moment about B. So by taking moment about, I am taking moment about B. So RA into this distance 6 minus 80 into 4 is equal to MB, moment at B, and this is minus 45.01. So I will get RA with this. Similarly, for knowing this reaction RB, I will take moment about this. So RA I have calculated here. So RA into this distance is 6 plus 5, 11, plus RB into 5 minus NT into this distance from here to here, it is 4 plus 5 will be 9, minus, because of this it will be 20 into 5 square by 2. So I will get moment at C, and what is MC? It is minus 54.06. So RA I have calculated here. So by putting this value RA in this equation, I will get RB. RB I will get. Similarly, RD I can find by taking moment about C. So if I take moment about C, then RD into this one is 5, this is second, minus 6 into 2, I will get MC, and MC is equal to minus 54.66. So RD will be calculated. So this is RD. Now this RC I can find by taking moment about B. So RD into 10 minus 60 into 5 plus 2 7 minus 20 into 5 square by 2 plus RC into 5 is equal to MB, which is minus 45.01. This RD, by putting the value of RD in RC I can find. Now RA, RB, RC and RD I have calculated. So if I want to know the check will be this total vertically downward load. This is 80 plus 20 into 5, 100 plus 60. So this total is 240. So 240 kilonewton is the total load which is acting downward. That should be equal to the total upward reactions. This should be equal to RA plus RB plus RC plus RD. And if it is 240, then okay. If it is not, then there may be some mistake. So this way we can check whether our reactions calculated is okay or not. So this way we can find the reactions, and reaction will be 45.83, RB is equal to 82.24, RD is equal to this one, and RC I can find by total load minus RA plus RB plus RD, otherwise by taking moment at B and then check it. So this is 98.5. So I can now plot the shear force diagram. This is my SFD. So this is the baseline, and RA is equal to 45.83. RA is equal to 45.83. So RA is equal to 45.83. RB is equal to 82.24. RC is equal to RD is equal to 13.08, and it is 98.85. These are my reactions. It means this is 45.83 kilonewton. This one is 82.24. This is 98.85, and this is 13.08. Now shear force diagram will be, this is the baseline, so it will go upward 45.8. So this is 45.83. Then since no load is acting in this portion, then again it will go 80 downward. So I will get minus 34.17. Then from this point to this point will be like this. Then again plus 82.24. So this will be 48.08. Then due to this load, this is 20 minus 500. So this minus 100 is equal to 51.93 minus. Then again plus 98.85. And from this to this it is constant 46.92. Then again minus 60. I will get minus 13.08. So that will be constant, and then again upward 13.08. This is plus, minus, plus, minus, plus, and this one minus. So this is my shear force diagram. So this is the shear force diagram. So, application of Clapeyron's theorems for fixed beam. Suppose I have a fixed end, then how can I apply the three moment equations? So, in this equation, what I will do, this is a fixed beam. So, if I want to know the application of three moment theorem, in this case, then I will extend my spans. I will extend this span. This is a imaginary span. This is a imaginary span of length 0, and this is A dash. This is A dash, and similarly, I will extend this fixed end of 0 span. This is a imaginary span, and this is a B1. So, 0 span I will extend it. Then this is the free BMD of this portion, and the distance of this from the centroid, suppose it is x left bar, and this is x bar right from this end. Then I will apply the three moment equations. If I applied three moment equations for this, it will be MA dash. I will consider these two span, this and this. So, MA dash into this length, which is 0, plus 2 times of this MA, plus this span, plus this 0 plus L, plus this is MB into this length, plus 6. This area will be 0. This is imaginary span. So, A1 x1 will be 0. Ax bar for this portion will be 0, plus A2 x2 for this portion will be, suppose this is Ax bar for this portion, and its distance will be from this one, from this is x1, and this is x2. So, this will be x right upon L1. So, L is this, that will be equal to 6 delta 1 upon, so delta 1 will be 0 since this span is 0, and if settlement is there, then okay, otherwise whole is 0. So, this way I will apply the three moment equation for A dash A and A B for these two spans. Then similarly, I will apply the three moment equation for these two spans, A B, one span this, and B B dash. For this span it will be so for AB and BB dash, it will be MA into this length plus 2 times of this into L1 plus L2. L2 is 0 plus this moment into its length. So, this is the imaginary span. So, this will be 0 plus 6 area of this into this distance. For when I consider these two span, so I will take centroidal distance from these ends. I will take this x left. So, x left upon this length for 2x A2 x2, for this will be 0 is equal to 0. No settlement is there. So, this way I can find the moment, and I will apply the three moment equations for fixed beam. So, Imagine a zero span to the left of A, zero span to the right of, applying 3 moment for this. So I will get this one. This will be my equation number 1. And for 2, it is there. So solving both the equation, I can find MA and MB. So let us do some numericals. A 3-span beam ABC has different moment of inertia, is loaded as shown in figure. Find the reaction and support moments. Draw the SFD BMD. So this is the case. So by applying 3-moment theorem, I have to calculate the moments at A, B, C and D and reactions also, and I have to draw the SFD and BMD. So similar case, first I will treat every span as a simply supported individual independent span and draw its free bending moment diagram. So this is AB. Treating it as a simply supported, I will draw the free BMD. So this will be, it is acting at the center, so it will be WL by 4, means 12 into 3 by 4. So it will be 9 kilonewton ordinate I will get. For this BC span, since no load is acting, so no moment, and for this it is a UDL, so WL square by 8, 4 into 3 square by 8, I will get 4.5 kilonewton. This is the maximum ordinate. So if I apply the 3-moment theorem for this portion AB, BC, then I will need AX bar. AX bar for this will be, area of this is equal to 1 by 2 into this 9 into this length. This is 3 meter. So this is the area, and its central distance between at the center, since it is symmetrical, 1.5, 1.5. So X bar will be 1.5. This will be AX bar for this portion. For this portion, it will be 0, since no bending moment is there, so this will be 0. Similarly, when I apply the 3-moment equation for BC CD, means BC and CD, then this will be AX bar. Of course, this is 0, and AX bar for this, it will be area of this. Area of this is equal to parabola 2 by 3 of this ordinate into this length. So this is the area, and it will act as the, it is symmetrical, so this distance will be 1.5 of this. So multiplied by 1.5, I will get AX bar for this. Then I will apply the 3-moment theorem. So this AX bar, it will be 20.25 for this portion, and for this portion it will be 13.5. So applying 3-moment theorem, in this case, as my moment of inertia is varying, so it will be MA L1 upon I1 plus 2 MB L1 upon I1 plus L2 upon I2 plus MC into L2 upon I2 plus 6 A1 X1 upon L1 I1 A2 X2 upon I2 L2, and no settlement, so it will be 0. Since my general equation is M1 upon E1 I1, it is E1 I1 upon E2 I2, and this is E2. So this is my general equation. Since E1 E2 is constant, so my equation will reduce to this one. So this is the equation that to be applied for knowing this. So MA is equal to 0. Since this is the simply spotted end, this hinge, so it will be moment at MA and MD, this is equal to 0. MA is equal to MD is equal to 0. This will be 0. So MA is equal to 0 plus 2 MB L1 upon I1. L1 upon I1 is equal to, this is 3 upon I is 2I. So 3 upon 2I plus L2 upon I. 3 upon 2I plus 4 upon I. So this I will get plus MC into L2 upon I. So it will be 4 upon I plus 6 A x bar for is 20.25 upon I1. I1 is 2I into 3. The length, this 3 plus Ax bar for this is 0. So this will be 0 is equal to 0. So this way I will get 11 MB plus 4 MC plus 20.25 is equal to 0. Then it will be 11 MB plus 4 MC is equal to minus 20.25. This is my equation number 1. Then again I will apply the 3 moment theorem for span BC and CD. For this span BC and CD, I will apply 3 moment theorem for these two spans. For this case, my Ax for this portion will be 0 and Ax for this portion will be same. So it will be MB into 4 upon I plus 2 MC into 4 upon I plus 3 upon 2I plus MD is equal to 0 plus 6 A1 x1 is 0 plus A2 x2 will be this one. So this will be my equation. So this moment is 0 and Ax bar is 0. So I will get another equations. So I have two equation now. This is my equation number 2 and equation number 1 is this one. So with the two equations I can find MB and MC, and that will be 1.607 minus and minus 0.643 kilonewton meter is MB. So these are the values. Now, so this is my fixed 1.607 hogging and 0.643 is this one. So this is my fixed BMD, and when I superimpose this fixed BMD on this, I will get this one. So this is the final BMD. This portion is sagging and this will be hogging. So this is the final BMD. For drawing the shear force diagram, what we require? I require reactions. So I have to calculate the reactions. Reaction when we can calculate. So let's take this is RA, RB, RC and RD. So taking moment about B, it will be RA into 3 minus 12 into 1.5 is equal to MB. MB is minus 1.607. So with this I will calculate RA. Similarly, by taking moment about RC, I can find RB. So it will be RA into this distance 4 plus 3 7 plus RB into 4 minus 12 into this distance. This will be 4 upon plus 1.5. So it will be 12 into 5.5 minus no load is acting. It will be equal to, and this moment is minus 0.643. So by putting the value of RA here, I can find RB. RA, RB I know, and this RC I can find. Suppose if I want to take the moment at this D, it will be RA into, this will be 4 plus 3, 7 plus 3, 10 plus RB into 7 plus RC into 3, that's minus 4 into, this will be 7.8.5 minus 4 into 3 square by 2, and that should be equal to this moment which is 0. So this way I can find RC. RD I can find from by taking moment about this. So it will be RD into 3 minus 4 into 3 square by 2 is equal to moment at C. This is minus 0.643. So this way I can calculate the reactions RA, RB, RC and RD. So if I want to check whether the reaction which I calculated is okay or not, what I will do? My total load is 12 plus total vertically downward load is equal to this 12 plus 4 into 3. So this is 24 kilonewton. That should be equal to the sum of the total upward reactions. So RA, this RA plus this RB, RC and this RD. So sum of RA plus RB plus RC plus RD, that should be equal to 24 kilonewton. That should be equal to this one. Means total vertical downward load should be equal to the total upward reactions. If these are equal, then it means okay. So this way I can calculate the reactions. So the reactions which I have calculated, so RA is equal to 6.77 kilonewton upward, RD is equal to 5.786 kilonewton upward, and RC is equal to this one, and RA, RB is equal to this one. So these are the values. RA is equal to 5.464. So this value of RA is equal to 5.464 kilonewton, and this RB is equal to 6.77 kilonewton. RC is equal to 5.973 kilonewton, and this RD is equal to 5.786. So now I can draw the shear force diagram. This is the baseline. This is 5.464. No load for this portion. It will go like this. Then this minus 12. 5.46 minus 12, I will get minus 6.536. From this to this, no change. Then minus of this plus this, I will get plus 0.241. So no load on this portion, so it will be constant. Further, there is a upward reaction, means this plus 5.97, I will get 6.214. And then for this portion is downward, so this minus 4 into 3, 12. I will get this one. Since it is UDL, so inclined 5.786, then it will go upward. This is my shear force diagram. This is plus, this one is minus, plus, plus, and this minus. So this is the shear force diagram. Let's take another numerical. For a two-span beam shown in figure, find the support moments and reactions and plot the BMD and SFDs. So in this case, this end A and C is fixed. So these are fixed end A, and what I will do? Same, I will extend it to A1. So this is my imaginary span of zero span, and also I will extend this one. Then I will apply the three-moment theorem. So first, what I have to do? I have to do its free BMD, free bending moment diagram. For this portion it is 0, since it is a imaginary span, and treating it as a simply supported beam. So my BMD will be like this. This is WL square upon 8. So 5 into 8 square upon 8, it will be 40 kilonewton meter. So this I will get. And for drawing the free BMD of this portion, so this is the simply supported beam, and there is a couple of which is acting at this one, 80 kilonewton meter, 3 meter, and this one is 2 meter. So obviously this will be, my reaction will be downward by taking moment at this. Suppose this is B, this C and D. So RB into 5, this should be downward to counteract this effect, minus this will be hogging and this will be sagging, 80, and that should be equal to moment at this is 0. So RB it will be 80 upon 5. So 16 kilonewton, and this will be a part of same magnitude, 16 kilonewton. So its bending moment will be like this. This is hogging. It will be 16 into 3, 48. I will get, and this is minus 48. So minus 48 plus 80, I will get 32. And this sagging, this is hogging. So this is the free BMD for this portion. Now area of this AX bar for this portion will be, what is the area? It will be 2 by 3 of this ordinate into this length. This is the area, and if I treat these two spans, then x bar will be same in both the cases. So it will be this one, and this is, since this is symmetrical, so it will be 4. So this way I will get Ax bar. This area is 0, and when I apply the 3 moment theorem for AB and BC, then this Ax bar will be same. Since it is symmetrical, this distance is same and this distance is also same. And for this portion, my Ax bar will be how much? It will be, I will consider it separately. So this distance should be from this end, from this end. When I apply the 3 moment theorem for AB and BD, then distance from this end, and for this span distance from this. So Ax bar in this case will be A1 x bar plus A2 x bar. Separately for this positive portion, it will be 1/2 into 32 into this length is the area. It will act at 2/3 of this distance. Since this is plus, so this will be plus, and this is minus, so the Ax bar for this will be minus. So it will be 48 into this length by 2. This is the area. It will act, so its distance from here, it will be 1/3 of this one, 1/3 of this 3 plus this distance. So this will be my Ax bar for this portion, and for first portion it is this one, and I will get, it will be minus 170, it is minus 26.667. So this is Ax left. Ax left means when I treat this span, so my this distance, this will be, and when I consider these two span, then x bar will be from this to this, and for this portion it is from this to this. Similarly, when I consider, when I apply the 3 moment theorem for these two span, BC and C dash, for BC and C dash with CD, no, BC and CC dash, then it will be for this, it will be when I apply the 3 moment theorem for these two span, BC and CC dash, this is the imaginary span 0. So for this case, my Ax bar for this will be, this is minus, so area of this will be 1/2 into 48 into this length into this distance, which will be 2/3 of this one. This is minus, and for this portion which is plus, area of this 32 into this by 2, this is the area, and its distance from this. So I will consider my central distance will be from this end when I apply 3 moment theorem for these two spans. It will be 3 plus 1/3 of this one, 1/3 of 2. I will get X bar. So let's apply the 3 moment equations one by one. First for this portion, so A dash A and A. So moment at this, which is 0, this into L plus 2 times of this into 0 this length plus this length plus moment at this plus 6 times of area of this 0 plus area of this upon length is equal to 0. Then I will apply the 3 moment equations for AB, BC. For AB, BC it will be MA into this length 8 plus 2 times of MB into this length plus this length plus MC into this length plus 6 times of AX bar for this upon L, and this case this X distance from this of course will be 4 plus this, and AX bar for this portion will be from this end, one from this end and this will be from this end. So this plus this, and this will be this one. Then I will apply the three moment equation for this BC and C dash imaginary span. BC and C dash. So then in this case it will be MB into this length plus 2 times of this MC into this length plus this length plus moment of this into this. This of course is a 0 into this length is 0. So it will be 0 plus 6 times of area of this upon L plus AX for this will be 0, and in this case my X will be from this portion. So this will be from this side, and for this portion of course it is 0. So this way we can apply the 3 moment equations, first for A dash AAB, AB BC, and then BC C dash. So I will get, if I apply for the first span, means for this one I will get these equations. This is my equation number 1. Then I will apply the 3 moment theorem for AB and BC, means for this AB and BC. So I will get this equation, and finally this is 8 MA plus 26 MB plus 5 MC is equal to this. So finally I will get this equation. So this is equation number 2. Then I apply the 3 moment theorem for this portion BC C dash. So for BC C dash it will be this one, BC and C dash, this span and this span, 0 imaginary span. So I will get another equations. So I have 3 equations. This is MB plus MC. In this case this is MA, MB and MC, and in the first equation it is MA and MB. So if I subtract 1 minus 2, equation 1 minus this equation 1 minus 2, what my MA will be eliminated. MA will be eliminated. So I will get equation in the form of MB and MC. So 1 minus 2, equation 1 minus 2 will be this one. I will get this equation. And equation 3 is mb plus 2 mc is equal to this. So now I have two equations, mb and mc is the variables. From these two equations I can find mb and mc. So mc is equal to this one, mb is equal to minus 6.564. So with this I will get mc, and by putting the value of mb and mc in this equation, by putting the value of mb and mc, I will get ma, and ma will be equal to this one, minus 36.78718 kilonewton meter. So these are my moments. So this is ma is equal to minus 36.7818, mb is equal to minus 6.564, and mc is equal to, this is plus 6.482. So mc is equal to plus. So my fixed moment will be like this. So at this is of course 0. So ma is equal to minus 36.78, and for b it's mb is equal to 6.564, means this one 6.564, and mc is equal to plus. These are minus and this is plus, so this will be here 6.482, means this is my fixed bending moment diagram. This will be hogging and this is sagging. When I superimpose this with this, my diagram will be, this is 36.78, 6.564, and this is plus 6.482. So my diagram will be like this. And this will be plus. I will get this diagram. So now this is my final bending moment diagram. This is the final BMD. For drawing the shear force diagram, I require reactions. Reactions I can easily find. So suppose this is RA, this is RB, and this one is RC. For finding RA, I will take moment out B. So RA into this length, and moment at this is minus 36 point. This moment is 36.78, and this moment is 6.564. This is hogging, and moment here is sagging. This is 6.482. This plus is sagging, minus is hogging. So RA into 8 minus 36.718 minus this 5 into 8 square by 2, I will get moment at B. MB is equal to minus 6.564. So RA I will get, and this will be, anyway, for finding RB I will take moment about C. So it will be RA into this length 8 plus 5, 13, minus this 36.78, minus this 5 into 8, and it will act at half of this is 4 plus 5, 9, plus RB into this length 5, and this moment is sagging in nature, so it will be same, so it will be plus 80 is equal to moment at C, and this is plus 6.482. So by putting the value of RA in this equation I will find RB, and RC I can find by taking moment at B. So RC into this length which is 5 plus this moment which is plus, and this is so this will be this sagging, and this will be minus 80. So in this case it will be hogging, and that should be equal to MB. MB is equal to plus 6.564. So RC I will find. Now RA, RB and RC. The sum of RA plus RB plus RC, that should be equal to the total downward vertically load, and this is 5 into 8 means 40 kilonewton. So that sum of these three reactions should be equal to vertically downward load. This is 5 into 8, 40. So in this case RA is equal to 23.769, RB is equal to 2.841, and RC is equal to 13.391. So the sum of RB is equal to 2.841. So sum of 23.769 plus 2.841 plus 13.91, that should be equal to the vertically downward load which is 50. So sum of these three will be 40. If this is the case, then it is okay, otherwise I have to check. In this case total reactions RA plus RB plus RC is equal to 40, which is exactly equal to the total vertical download which is 5 into 8, 40. So it means my reactions are okay. So now I can draw the shear force diagram. So this is my baseline. So this will be 23.769. Then there is a UDL of 5 into 8, 40. So this minus 40, I will get minus 16.231. And from here to here, no vertical load, so it will be constant. Oh no, it will be a jump of 2 points. So minus 16.231 plus 2.841. This reaction, so I will get this one. So this is 13.391. and from here to here it will be constants. Then this reaction is 13.391. So this will be my shear force diagram. Of course, this will be plus and this is minus. So this is my shear force diagram. So this is now the end of the question. So thank you very much for listening. So this is the end of the lectures. So thank you very much. I hope you enjoyed my lecture. Thank you.